Pleasant day to everyone. Today we're going to discuss part 5 of Module 1 of the subject CE2131. So in this part of the module, we'll be discussing earthquake. So basically, when we talk about earthquake, this is simply any sudden shaking or movement of the ground which is caused by seismic waves that moves through within the earth surface or earth rocks. So earthquake usually occurs along geologic faults, and the release of sudden and extreme energy will be the reason why we feel these earthquakes. And this energy is caused by the shifting or movement of the Earth's crust or your plate tectonics. So seismology is the study of earthquakes and the propagation of the seismic waves within the Earth. So usually, under seismology, this will now include both naturally caused and artificially produced vibrations or movements of the Earth surface. So since earthquakes happens along faults, we now define faults simply as the narrow zones wherein rock masses would be moving in relation to one another. So their movement could be lateral or perpendicular to each other. So a fault now may either be a planar or a gently curved fracture in the Earth's crust. And in here, compression or tensional force will be causing displacement of the rocks or of the plate opposite the side of the fracture. So the faults now may either be vertical, horizontal, or inclined at any angle. So we have different classification of faults, and the classifications now will be dependent on the angle of the fault with respect to the surface and the direction of the slip along our fault. Okay, so basically we have two general classifications of faults. The first one is what we call the deep slips, and the other one is what we call your strike slip. So what's the difference between the two? For deep slips, they are now faults that would be moving along the direction of the deep plane area, while strike slip will be moving horizontally past each other. Okay? And under the two general types, we also have their subcategories or subtypes. So under deep slip, we have what we call the normal slip and the reverse slip. And under the strike slip, we have what we call your sinistral strike slip, and the second one is what we call your dextral strip. A special classification of fault is simply a combination of a deep slip and a strike slip, which we call an oblique slip. Okay? So to understand the different classifications of faults, let's start first with the deep slip. So the first one is what we call the normal fault. Okay, so a normal fault basically will be two blocks that will be moving against each other. So the upper block, which is what we call the hanging wall, will be moving downward relative to the block below, which we call the foot wall. Okay, so they are moving vertically and towards each other. So this would usually be occurring in response to extensions of the other plates or other blocks of the fault. So this is usually observed along ocean ridges. Okay, so here is a figure that would explain normal fault. So as you can see, the two blocks on the opposite side of your hanging wall is moving away from each other. So as we have learned from physics, any force that moves away from each other will experience tension. So since they are moving away from the middle block, which is our hanging wall, then it now goes down. So it moves down as they stretch away towards or away from each other. So that's for normal fault. So we have here an animation of your normal fault. So as you can see, so we have your hanging wall that is moving downwards, while the foot wall will either be moving towards this direction, thus making the hanging wall move down. Okay. So next we have your reverse fault. So from the name itself, reverse, it is simply the reverse or the opposite of a normal fault. So instead of the block above or your hanging wall moving downwards, the upper block now will be moving up and over your lower block. Okay, so the reverse fault will now be usual in areas of compression. So this will be basically more evident on converging boundaries. If you could remember that in our module 1 part 2. Okay, so when the deep angle now between the two blocks or two plates is shallow, the reverse fault now is referred to as a thrust faulting or a thrust fault. So this is a diagram of the reverse fault. So as you can see, the blocks beside or the plates beside your hanging wall is moving towards each other, thus compressing our hanging wall. So because of that compression, our hanging wall now is moving upwards, and at the edges, it's moving above or over your other plates. So here is an animation of your reverse fault. So as you can see, they are moving against each other like your convergent boundary. Okay? And one of them is moving upwards. So that's a reverse fault. So basically, the movement of the plates or of the blocks is perpendicular to the fault. Okay, so that's for deep sleeps. So we have the second classification of fault, which is your strike slip. So for strike slip, it can either be a sinistral strike slip, which is also known as your left lateral or your left-handed fault. Okay, so this happens now when the far side of the plate or of the block will be moving towards the left direction where you are observing or standing. The second classification under strike slip is what we call the dextral strike slip, or also known as the right lateral or the right-handed fault. So basically, it's opposite the sinistral, therefore the movement of your blocks or of your plates will be towards the right. So when you observe the movement of the fault or of the plates, when you're standing in front of them or any part of side of the fault, you will see a rightward movement. So basically, for a strike slip, this is now an example of a fault that would be seen on normal boundaries. Okay, so as you can see here, diba? So they are moving past each other. So basically, the boundary between them is a transform boundary. So they are moving parallel to the line of the fault. So in this animation, this is now an example of a left lateral or a sinistral strike slip. How did that happen? So if we are standing on this side, okay, if I'm looking towards the other side of the fault now or the block now is moving towards the left side. Okay, so if I am standing at this side of the fault, then what I will see is that the other side is moving towards the left. So it's a sinistral strike slip. So we have here a figure that would differentiate your sinistral and dextral strike slip. So as you can see, if you're standing here, the movement of the other plate is to the left. If I'm standing at the side, then the movement of the other fault or of the other plate is also to the left side if I'm facing this one. So likewise, for dextral slip, if I'm standing here facing the other block, then I would see a block that is moving towards the right, and the same, if I'm standing here facing this block, I will be seeing the block or the plate moving to the right side. So wherever you are, which side of the plate you are, what we will observe is the direction of the plate that is moving. So if you see it moving to the right, then it is a dextral slip. If you see the plate moving to the left, then it is a sinistral strike slip. Okay, so the special kind of fault that we have is your oblique slip, which is simply a combination of dip and strike slips. So an example of this is the rupture of the Wairarapa fault in 1855, which was a combination of reverse and dextral movement. So to understand oblique slip, we have this animation. Okay. So this one is an example of a, so downwards yung hanging wall, so it is a normal slip, and if I'm standing here, the plate is moving towards the left. So it's a combination of normal and sinistral slip, this animation. So as you can see, as if you have seen it or watched it, this plate, the hanging wall, has moved downwards, and at the same time, it moved towards the left side of the foot wall. Okay, so it's a combination of your strike slip and dip slip. Okay, so these are parts of our plates that we consider when we study faults. So basically, we have your hanging wall. So the hanging wall is the one that the movement of the hanging wall will define what kind of fault we are looking at. So if the hanging wall moves down, then it is a normal fault. If the hanging wall moves up, then it's a reverse fault. So if the two plates, two blocks are moving past each other, then it's simply a strike slip. So depending on the direction, it would either be sinistral or dextral slip. Okay? So in relation to earthquakes, we have what we call the Pacific Ring of Fire. So probably you have experienced earthquakes throughout your life. So as you can see, the Philippines is within the highlighted portion of this map, which represents now our Ring of Fire. So since the Philippines is along this Ring of Fire, that explains now why we in the Philippines would always experience earthquakes or volcanic activities, especially in Mount Mayon and Mount Pinatubo. Okay? So to understand the Ring of Fire better, let us watch this simple video.
There's one thing you need to know about the Ring of Fire. It produces 90% of the world's earthquakes. The Ring of Fire includes about 450 volcanoes. Many of them are submarine volcanoes, meaning they're underwater, as are 75% of the world's volcanoes in total. Now, the Ring of Fire is also called the Circum-Pacific Belt. It's the result of plate tectonics. The movement of the plates has created a nearly continuous series of oceanic trenches and chains of volcanoes stretching for 25,000 miles in a horseshoe-shaped pattern from New Zealand past Japan, across the Bering Strait, and down toward the tip of South America. The plate movement also causes earthquakes. Because many of these earthquakes occur in the ocean, the Ring of Fire is also known for tsunamis, produced when the ocean floor is either forced to rise or fall. When a megathrust event happens in this region, the water is displaced and the water pushes ashore. Most tsunamis are only a few inches high, but there are times that that wave and that swell can be as tall as buildings.
So from the video that we have just watched, the Pacific Ring of Fire, which is the series of volcanoes along the Pacific Ocean, would basically be related to earthquakes, since the volcanic activities are caused by subduction of plates or the movement of your plate tectonics. And whenever these plates will be moving, it will now result to earthquakes. So when we talk about earthquakes, basically you will always hear the words focus and epicenter. So what is the difference between the two? When we say focus, this is simply the point wherein the actual earthquake happens or originates. Okay? While epicenter is simply that spot or point right above the focus of an earthquake. Okay? So in this image, we can see here your focus. So this is where the energy started. And then right above it is our epicenter. So we also have what we call magnitude and intensity. So magnitude would simply be a measure of the size of the earthquake from the source. Okay, so it's a quantitative measure. So it is measured in terms of the strength of the earthquake or the total energy that it has released. While intensity also measures earthquake, but it would be a qualitative measure of the strength of the earthquake. So it means it measures how severe the effect of the earthquake in the surroundings. And for intensity, it will now be measured based on the location of the observer or of the one experiencing the earthquake. Okay? So magnitude, it's measured at the exact point of the earthquake, while intensity is measured and is dependent on the location of your measurement. So since we measure earthquake with regards to its magnitude or intensity, which are both different ways of measuring and defining the earthquake, we will now have two different ways of measuring the earthquake. So in terms of the intensity, we now use the modified Mercalli intensity scale, which simply measures the intensity of an earthquake by observing the effect on the surrounding. So it means it will now include its effect on people, the environment, and the Earth's surface. So the modified Mercalli scale will usually be in terms of Roman numbers 1 to 12, and for each number, it will now define the effect of the earthquake. And then in regards to magnitude, we have what we call the Richter magnitude scale. So this one will measure the energy that is released by an earthquake using a seismograph. So the Richter magnitude scale would now assign numbers from 1 to 10 in order of the increasing intensity or increasing release of energy. So in comparison now, or an analogy for magnitude in intensity would be a ripple of or a drop of water. So The drop of water will be the cause of the vibration. So this is your focus or the specific spot where the vibration originates. Okay, so from here, magnitude now will remain the same wherever we are observing. Okay, so the numerical value of the magnitude will remain. And then the intensity now will vary depending on the location of your observation. So meaning, the more you are near the focus or the epicenter, the higher the intensity you will experience. And as you go further away the epicenter, less na yung effect ng earthquake sa'yo. So as you can see, for the magnitude at any location, let's say it will be 6.5. But the intensity now for different locations will be different. So if I'm at this point, the intensity will be 3 or higher. And then farther away will be 1, which is lower experience or lesser effect on that point or on this point. Okay? So to understand the difference between magnitude and intensity, let us have a comparison of the different scales that we use to measure the earthquake. So we have here your modified Mercalli scale, which is for the intensity, and we have the Richter scale for the magnitude. So under the modified Mercalli scale, we have 1 and 2, which is felt by almost none or felt by very few. So the modified intensity scale 1, 2 is almost similar or equivalent to that of a 2.5 magnitude in the Richter scale, which is defined as generally not felt but is recorded on seismometers. So the next one is we have 3, 4, and 5, which is an earthquake which could be felt already by many, though will not be able to realize that that tremor or vibration is an earthquake, up to a earthquake which is felt nearly by everyone, and when you are sleeping you'll be able to wake up because of the vibration. So an equivalent of intensity 3, 4, and 5 in the Richter scale is a magnitude 3.5. So it simply defines that a magnitude 3.5 is felt by many people already. So next we have intensity 6 and 7. So it's everybody now feels the earthquake. So their initial reaction is to run outside in order to avoid falling furnitures or fixtures inside the house or the building. So in intensity 7, built structures now that have poor foundations and design would be damaged, while some will have a very slight or small and negligible damage. So for intensity 6 and 7, this is now equivalent to a Richter scale magnitude of 4.5. So a magnitude 4.5 means there's local damage already that could happen in the area in which you are experiencing the earthquake. Then we have intensity 8 and 9. So there's already a damage to specially designed structures, though minimal lang siya. And then for intensity 9, there's considerable damage already and there's a shift in foundation, meaning the foundation could have slipped off already, bumaba yung ibang parts ng foundation ninyo. And there's a noticeable cracks already on the ground or on your roofs. So an intensity 8 and 9 will be equivalent to a 6.0 magnitude on the Richter scale. So this is now defined as a destructive earthquake. So a magnitude an earthquake with magnitude 6 will be defined now as a destructive earthquake. And then we have intensity 10. So many structures now, kahit na maganda ang design, usually will have some destructions, and then the ground will be badly cracked. Okay, so this is now equivalent to a major earthquake having a magnitude of 7. And the last range for the intensity is intensity 11 and intensity 12. So almost all structures have fallen already, or there is already a total destruction. And you can see waves on the ground surface. So an intensity 11 or 12 will be equivalent to a magnitude 8 and above. So earthquakes that have magnitude 8 and up are considered great earthquakes. So earthquakes are caused by different factors. The first one is due to superficial movements. So these are now feeble earthquakes that are caused by superficial movements, such as the dashing waves that causes vibration along the seashore, or water descending along a high waterfalls that impinges the valley floor and causes vibration along the neighboring areas. So this could also include at high altitudes when snow falls down an avalanche. So these are now superficial movements that when happens will cause a very small earthquake. Okay? So the next cause of earthquake are your volcanic eruptions. Okay, so this is the more familiar to us compared to the superficial causes. So volcanic eruptions would cause feeble tremors in the surface of the earth and would cause severe vibrations on the adjoining area and would usually have disastrous effects, since aside from the earthquake, there would also be lava flow that you have to consider when there is volcanic eruptions, as well as the pyroclasty emissions and the ashes. Okay? And the most common cause for earthquake is due to folding or faulting. So this is caused due to the folding of the layers of Earth's crust. So from the word fold, we could see that the surface or a layer of the earth would technically be folded. Okay, so these are more disastrous and are known more as tectonic earthquakes. So they are either directly or indirectly cause of the change in the structural features of the earth's crust. So an example of that is this one. So as you can see, we have your plate here, so it's moving and being folded. So it's not actually moving, but instead it's being folded. So that's what happens at one moment on your earthquakes. So earthquakes now could be classified into three depending on the depth of the focus, the cause of the origin, and the intensity of the earthquake. So under depth of focus, we could now classify earthquake as either shallow earthquake, which would usually lie anywhere up to 50 kilometers below the surface, or an intermediate earthquake, which would lie from 50 to 300 kilometers below the surface, and a deep-seated earthquake, which is found 300 or lower than 300 in the surface of the earth. And then for the cause of origin, an earthquake could be called a tectonic earthquake, which is due to the folding or the faulting, the movement of your plates, or a non-tectonic origin. So this would usually be due to volcanic eruptions, your landslides, or your superficial cause. And under intensity, we now have classified it using our Mercalli scale, which was initially given by the Rossi and Ferrell, which was only scaled 1 to 10. And then, for intensity, as we have defined, it is based on the sensation or the experience of the people and the damage that the earthquake has caused. So it was later modified by Mercalli and was later again modified by Wood and Newman. Okay? So what are now the engineering considerations for us when we talk about earthquakes? So basically, the time and intensity of earthquake can never be predicted as of now. But there are some innovations already or inventions that are trying to anticipate when an earthquake will come. So that would be very helpful later on during our design or planning of a site or of a building. So the remedy for us now, since we can never predict when and where an earthquake will happen, is to provide additional factors in our design of structure in order to minimize the losses due to shocks of an earthquake or minimize the damage that our structure would experience. So an example of this remedy and additional factors could be taken by collecting sufficient data regarding the previous seismic activity in the area. So example, your location A has always experienced earthquakes of magnitude 6 or 6 to 7 every 3 years. So you have to expect that that area would basically be experiencing more earthquakes or usual earthquakes of 6 to 7 magnitude. So therefore, based on that data that you have collected, then you design your structure that could be able to withstand that magnitude and withstand the occurrence or the frequency of the earthquake. So also, you have to assess the losses which are likely to take place in the furniture due to earthquake shocks. So since you have collected a data that location A always experiences a 6.6 to 7 magnitude, then probably you have to design that the furnitures on your structure would instead be built in instead of those movable furnitures, which could again affect your design. So aside from that, you have to provide factors of safety in order to stop or minimize your losses due to severe earth shocks. Okay? So kung yung design mo is nasa, let's say, 200. So ang safety factor mo, taasan mo pa yung 200 na design mo. Ibig sabihin, pag tinaasan factor of safety, tataasan mo yung kakayanin ng structure design. So our precautions now to make the building or structure an earthquake resilient building, one would be make the foundation rest on a firm rock bed. Okay, so do not put your structure on a layer of sand or of a layer of soil that is very easily loosened when there is an earthquake or when there's a vibration. So for this, you could apply grillage foundations. Okay? Another, excavation of foundation must be up to the same level throughout the building. Then concrete should be laid in rich mortar and should be continuous. So masonry, as much as possible, must be in a maximum ratio of 1:4. And then your reinforced concrete cement slab should, for cantilevers, projections, parapets, and domes should also be provided. So basically, all parts of your structure should be reinforced. And all parts of the building must be tied firmly with each other, meaning the connections between the parts of your buildings should be stable. And also, your building should be in uniform height. So, walang mas mataas, walang mas mababa. Okay, so basically, the moment of your building should satisfy the or be able to withstand the earthquake. Also, you have to consider the materials that you are going to use in your construction. So some of the significant earthquakes in history would include the 1960 Valdivia, South Chile earthquake with magnitude 9.5. This is the strongest and most devastating earthquake recorded ever in history. Also, we have the 2004 Indian Ocean earthquake. This caused the worst tsunami in history. It is a series of earthquakes and tsunamis having a magnitude of 9.1 to 9.3. So this is the third largest earthquake recorded. And then we have 2011 Tohoku earthquake and tsunami. It recorded a magnitude of 9 and it has a surge height of 133 feet above sea level. So it is one of the famous and most significant earthquakes that happened internationally. Okay, so it's among the top 10. So these are three of the top 10 strongest earthquakes that happened all throughout the world. And then in 1976, we have the Moro Gulf earthquake and tsunami. This is the strongest earthquake that hit the Philippines. So its epicenter was recorded at the Celebes Sea with a magnitude of 8. And then in 1990, we have the North Luzon earthquake, which is the most popular earthquake in the Philippines. It happened alongside the eruption of Mount Pinatubo. So its magnitude was recorded at 7.8 with maximum intensity of 9. So we have Cabanatuan City and Baguio City incurring the highest number of casualties. So there were survivors that were rescued almost 3 weeks after the earthquake happened. So to have a better and further understanding of earthquake, let's watch the following videos.
The ground starts to quiver, glasses rattle. Soon, walls shift and everything begins to collapse. Telltale signs of what could be a devastating earthquake. We've seen the destruction they unleash. Some of us may have even lived through one. And we know they can be deadly. But where does this mountain-moving force come from? While we may think we're standing on solid ground, the Earth beneath us isn't completely stable at all. Our planet's crust is made up of about 12 major tectonic plates that fit together like a giant jigsaw puzzle. These huge slabs of land float on superheated magma and constantly shift, bump, and grind against one another. It's there, along the seams, where earthquakes tend to happen. When friction between the two plates is violent enough, seismic shock waves ripple through the ground, rattling everything that stands on it. The stronger and shallower the quake, the more violent the destruction. The most violent type of earthquake is born in a subduction zone, where one tectonic plate is shoved beneath another. While one plate is forced downward into the mantle, the other jets upward, often violently. This is the type of quake that rocked Nepal in May 2015. And when subduction happens under the ocean, it can create giant, unstoppable waves called tsunamis, like the ones that killed hundreds of thousands in Japan and Indonesia. On average, earthquakes kill about 10,000 people each year. Sometimes numbers are far higher. The quake that hit Haiti in 2010 killed more than 300,000 by some counts, making it one of the deadliest on record. It is estimated that there are 500,000 detectable earthquakes in the world each year. 100,000 of these can be felt, and 100 of them cause damage. That's about 0.1%. The magnitude of an earthquake is measured using the Richter scale, which runs from 0 to 10, 10 being the strongest. Every whole number increase on the scale means 10 times more ground motion change. In recorded history, the world has never experienced a 10 on the Richter scale, but scientists predict an average of at least one major quake of magnitude 8 or higher every year. The fact is, the Earth's crust is restless and always on the move. We can't see earthquakes coming, but we can prepare for them. Engineers are now designing stronger buildings, resilient enough to survive a direct hit. Scientists are crunching data to project the power of future quakes and anticipate when and where they could strike next. Right now, we can only estimate the probability an earthquake will occur, but perhaps one day we will learn to predict them, minimizing their destruction and saving countless lives.
So from what we have discussed and what you have watched, basically you have learned already what is the importance for us as engineers to understand and be knowledgeable of earthquakes. So that's it for part 1 or part 5 of module 1, earthquakes. Thank you for listening.